So I'm going to talk about the transport of the subtropical gyre in the South Atlantic from the three-dimensional velocity field that I presented before, based on Argo and Altimetry. And I will go a little bit beyond the subtropical gyre, but it will be mostly the subtropical gyre. Basically, what I'm going to look at is what is the vertical structure of the circulation in the subtropical gyre, and what are the zonal volume transports in the gyre. Then I will also look a little bit at the meridional transports in the interior, and also a little bit in the western boundary current, in the Benguela current. And I will look a little bit along at the structure of the flow along the eastern boundary. So that's the main topic I'm going to look at. So the data sets are the profiles from the Argo flow, from the Argo GDAC, from 2000 to 2012. Then there are the trajectories, both from Argo flows and some host flows. So that's 1990 to 2013 roughly, until March. Plus there is the sea surface height from Aviso from 2000 to June 2012. And then for the Ekman transport, I need wind field, so I chose to use the NSEP reanalysis too. And from the Argo flows, I derived the dynamic height for each profile. And then I correlate, this looks really weird. Yeah, okay. Then I correlate the sea surface height and the dynamic height at every depth. And that way I can get a dynamic height, synthetic dynamic height from the sea surface height. Now this figure on the right shows the correlations, which are mostly pretty good. So they are, in large parts of the, especially the subtropics, they are more than 0.6 or even 0.7. A little bit less well, like down in the southwest corner, but most of the areas it's a very good correlation. And then in the lower right is an annual mean dynamic height only from Argo at 1,000 decibel. And then on the bottom right is the same field, but from the synthetic dynamic height. And so they look very similar. And of course on the right I don't have all the gaps that I have on the left. So that's the good news. I like it. So I continued working on this. And then here I used dynamic height field to get all the geostrophic velocities from the synthetic dynamic height. And on the bottom left, we can see the geostrophic velocity relative to a level of no motion at 1,000 decibel as a zonal component for January 2011. And you pretty much see pretty nicely the circumpolar current at the bottom end, but it's kind of weak. And of course, we know 1,000 decibel level of no motion is not a very good one. So, but we do have the subsurface velocities from the flow to calculate the reference velocity at intermediate depth. And that's basically shown at the top right, the reference velocity from all the flows drifting between 800 and 11,000 decibel, 1100. And that velocity field has been used to correct the velocity at every level, and the corrected velocity at 20 decibel is shown at the bottom right. It shows a much stronger circumpolar current going to the east, a much stronger South Atlantic current going to the east, near between 35 and 40 south. It also shows very nicely the Agulhas current and the Agulhas return current. It shows the westward flow north of the South Atlantic current, predominantly westward flow. So this is pretty nice. And on the next slide, I show the same thing for the meridional velocity. And the main difference is the adjustment is again in the southern half of the domain, basically south of 30 south, especially in the boundary current. For example, you can see the Meridional current in the bottom left panel is pretty weak, and in the bottom right panel is nice and strong. And that's thanks to the subsurface velocity we can measure from the flow directly.
Claudia, you didn't mention where you got the reference velocity.
Right, from the Argo floats and the boat floats, drifting between 800 and 1100 decibel.
You're doing that yourself?
I'm doing that myself, yes. And I gave a presentation on that, so I was hoping I can skip it, but I'm going to expand on this. So basically what I'm doing is I take the surface drift from the Argo floats and extrapolate it to the actual arrival at the surface and going back down from the surface position to get a better estimate of the subsurface drift. So if you just use the measured surface positions, you will have an error of approximately 10% or more, depending on how strong the surface currents are compared to the deep currents. So if you do that correction, you get a better velocity. And then you pick all the ones at the level that you want to use at the level of no motion within the depth range of it, and you average them all together, and then you have a subsurface velocity field.
So the manual reading.
But you can use the local estimate, and I do it when it exists. But where it doesn't exist, I have to revert back to the monthly climatology, not the annual climatology. So. Then before I go to the layer by layer looking at the flow, I just wanted to show a quick, what are the water masses in the subtropics from Peterson and Whitworth, very old, but it's still true in general. So I have a couple of layers in the upper layer and the thermocline above the intermediate water level. And I have one layer that represents intermediate water, and I have two layers that together represent the upper circumpolar deep water between 1100 or 1200 and almost 2000 meters. So now, near surface, very messy slide. I tried to put on the new results and two older results at the same time. So essentially, we know what the subtropical gyre is supposed to look. If you look at the two panels on the left, they are from different studies doing it in different ways, but they look pretty similar in a way. You get a nice subtropical gyre, and there's these smaller velocity loops inside. And one of them represents the upper 100 meter, the top left from Stromer in England, and the other one is only the surface flow. So that makes them a little bit different. And then on the right, we see the surface to 100 meters with and without Ekman. And so I will pretty much focus on the one with Ekman. But the main difference between the two is in the northern part where you have this meridional component from the Ekman. So you see a lot of blue, and blue means there's a slight southward component of the current, whereas red means there's a northward component of the meridional flow. So the Ekman creates the southward rotating of those vectors, but mainly they go to the west, most of them. And basically the interesting part, aside from I've seen the gyre and the boundary currents, are those vectors in the middle here, where you see the northward flow inside of the gyre. Not so much the way it was shown over here by Rio, over here it's mostly on this side, but actually it's quite far to the east. You get these bands of northward flow. And one thing I didn't mention here, thanks for that slide. So there's the predominant westward flow here between 10 and 20, and then there's another area, there's kind of significant westward flow over here. And that was mentioned before as the double gyre structure. And here's an example from 2011. And they showed the same thing pretty much. You have westward flow up here around 18, 19, 20 south, and then you also have westward flow around 30 south. So I'm seeing the same thing in the data I put together from Argo and Altimetry. Now if we go a little bit deeper, and here it becomes even more complicated. I did 200 to 400 meters as the upper thermocline. The Storm in England did 100 to 500 meters, so that's pretty much most of the thermocline. And for Reed, I only have the 250 decibel. But they still look pretty similar. So you've got a narrower subtropical gyre here. So the basically the southern tropical cone shifts south. And you can see that in all the figures here. You see this cone more in the south. Before it was more up here, and now it's down here. And you also see this one. A double gyre structure. But you don't have the eastward flow in between those two westward flows anymore. And if we go deeper, we see even more squeezing. So this is basically a lower thermocline. This one is a very thick layer actually. But we see the relatively narrow subtropical gyre in all of these. And you still see this diagonal flow going north as well. It's a very narrow flow here. So now we go to the intermediate water layer, where the gyre comes more narrow, and so, and we actually also have an eastward flow right here, which was shown before. Also right here we got this eastward flow, and here you don't see it. And here you don't see it. But here you see the 20,000. So it's a little bit higher resolution than what they could do before. And then we go to the circumpolar deep water, and we start seeing less significant westward flow here, so it can be really weaker. Here, this is at the bottom end of it, so this is 2,000, rated at 2,000. So he basically almost already shows most of the deep water here. So these two is very difficult to compare because it's almost like a different element. These are still compared pretty nicely. You've got this westward flow here, you've got the westward flow here. And then here he didn't really have much data, so some of the lines here are dashed in his plot. But I'm focusing on the gyre. So he does have this gyre, even if it doesn't seem to be flowing here. There are no observations here, so who knows what it does. So now I look at the transport of the South Atlantic current. The southern boundary of the current is basically the subtropical front, and it's pretty commonly assumed that that front is at a latitude where the salinity equated is very large, where the salinity is about 34.9. So I chose the 34.9 is the subtropical front. The northern boundary of the South Atlantic current, that's the latitude where the velocity changes from eastward to westward. And so in all the panels over here on the left, it's basically from the upper ocean down to the intermediate water. We see this pretty strong increase of the transport by almost like a factor of 3, or even more than 3. And we also see an increase in the next level between 1,200 and 1,600 meters. And then below 1,600 meters, there's a little bit less of an increase, but there still is some increase here. And then going more west, it drops off again. Everywhere. Except for this one, the drop off is a little bit weaker, and everything is a lot more noisy. And basically, what happens is that the width of the current changes quite significantly depending on the position of the subtropical front. And also we have the subsolar in here, so that squeezes the current together. And there's a pretty high correlation in all the 5 layers between the width of the current and the transport. It's 0.78 at the surface and 0.73 in the deepest layer. So it's kind of go to the westward branch of the subtropical gyre, so the southern south equatorial current. In the first three layers, from the surface to 700, we see an increase as well from the east to the west. But we don't really see this drop off, except here at the very boundary, and here it's stable and here it's stable. Now the width of the current increases a lot and then it becomes stable. And here it was actually quite difficult. The southern boundary was easy to find, whereas the boundary of the South Atlantic coast. The northern boundary is a little bit more difficult. If you have a velocity sign change, it's easy to find. But in some of the longitudes, the velocity never goes from westward to eastward, but there is a significant velocity minimum in the westward transport. And that's what I said in the latitude, where the northern edges of this curve. So we also see how the current gets narrower and narrower as you go deeper. And then in the deepest two layer, it becomes a lot more complicated. We don't really have much of an increase, but it's a lot, very, very messy. And part of the problem is it becomes, the deeper you go, the more difficult it becomes to define the northern edge of the curve here. So we have good correlations on the left three panels with 0.9 in the upper layer and 0.75 in the deepest layer between the width of the current and the transport in the current. And then very poor correlations over here. Everything is a lot more noisy, much larger standard deviations of the velocity of the transport. But that's what the ocean tells me from the data we have right now. So then I wanted to see, well, how does the gyre transport flow? And that's very difficult to do because here I took the northward transport at 35 south. But essentially you would have to go to different latitudes depending on which longitude you're at. But I was really interested in finding this guy between 0 and 19 and see if this one, the northward transport, kind of balances with the change in the eastward transport here and the westward transport here. And most of the time it balances within the arrow bars, which is kind of large, but not larger than the single. So it only floods except for the deepest one here, the deepest two actually. In the three layers here it balances quite well, in the deeper ones it doesn't. And I'm not surprised because the zonal transports are not very stable either. So, and here, in an earlier work, just based on subsurface velocities only, there was the question, well, here it goes from 26 to 19, what happens to the 7? Maybe it goes along the subiolar 8, or maybe it goes this way. I didn't know at that time. Now I actually tend to think most of it goes along the subiolar 8. And then here, it didn't show much here, but we didn't have that much data in between here, so I couldn't see the northward flow here. So now I'm looking a little bit at how well can I do the western boundary transport of the Benguela current. So that's again climatological transport for the 0 to 800 meter layer on the left, and this is the 0 to 2,000 meter for the full length of the data set. And then I put some dots that I found in literature here. Red for the 0 to 200 is off my scale. And then the blue transports here are all higher for the 0 to 800 meter layer than what I got here, except for this one is pretty close. Now, of course, they were done during a different time period than my observations, plus they are snapshots, and I have long-term means. And the other thing is, of course, they can catch that little piece that is on the shelf of the Benguela current that I can't catch with my data. And so considering that, I think I'm pretty happy with what I can do. I can't get that piece on the shelf, but I can get a pretty decent transport estimate. And I actually think that the increase, the gradual increase, the increase could be realistic And part of it has to do with this recirculation of the Benguela current, where it flows back to the north and joins the Benguela current again. And that's where you get the highest transport, where this return flow joins the actual Benguela current flow. So now we go to the east for a little bit. And here I wanted to see, earlier work showed this forward undercurrent along the eastern boundary. And there will be another slide following this one to show what was shown before. But what I see here is in the salinity and intermediate water level, so it's the salinity minimum water, there's this water that seems to be going south along the coast here, along the shelfway. There even is a little bit more saline water here. Now, does it come from the Indian Ocean or does it come from the north? I don't really know for sure. And of course, here's the Benguela Current as well. This is just a pressure field that goes through the field, so it doesn't say that much. And here's the velocity field that goes with this. And there are these little areas of sulfur flow, but it's not very conclusive. And down here, but there is some indication that at the intermediate depth, there is the potential for not quite a current, but a significant southward transport on average. And here, here it looks like it goes maybe even to 34 south right here, which is where it's broad, which was higher salinity. And Richardson and Garzoli reported extended periods of southward drift by some flows in that region for a period of 3 to 16 months. And they happen to even go further south, all the way to 36 south. At least one or two of them did. So there must be something going south sometimes that brings this more salty intermediate water to the south. And here is a look at the different depth levels again, 200 to 400, 400 to 800, 800 to 1200. So this one I already showed more or less, because this is almost the same as the core layer of the intermediate water. And here we see the southward drift a little bit, and here even detail a tiny little bit. And an earlier work here by Rachel of 2010 showed the forward undercurrent like this at 100 to 500 meters. So it's kind of this layer and a little bit into this layer. And what happens with the current afterwards? They show it going offshore. Well, maybe it's still going offshore and also going deeper, and sometimes continues south, and sometimes it doesn't. Who knows? Right now, I think we don't really know. So this is kind of a summary slide of all the cones and the width of the cones in color-coded from 0 to 400 meters, and then how the cone shifts more south and it goes deeper. And black is basically the names of all depth levels down to 2000. And these dashed lines here, that's pretty much the boundary of the South Atlantic cone, independently of the depth. And for the South Equatorial cone, the boundary of the cone shifts south, the northern edge of the cone. And then a little forward undercone with a couple of dots. How far does it really go? And if it goes deeper and it's the same cone, it just gets pushed to the deeper layer. I should have put a question mark there. But that's pretty much the result of the whole flow field. And so this is basically a summary slide. The graphical summary slide we just saw, now this is the text summary slide. So the subtropical gyre, well, follows the usual pattern that we already know, but it provides a little bit more detail now in the new plot. And it clearly shows the degrees of its meridional extent with increasing depth, the southward shift of the South Equatorial current. I didn't talk much about the highly barotropic Sapiola eddy, but it's clearly reproducing the same set, and it was shown in many earlier studies, and here are just two of them. I do get a sign of this double gyre structure, which was also reported in an earlier work. And it could be that it doesn't just show up at the surface, but it could extend down to maybe 400 decibar or maybe even deeper. And so when we get more data, we could get a clearer picture on how deep that structure goes. Then I has nice eastern and western boundary currents, if a little bit weaker sometimes than they should be, especially with the Brazil current at certain latitudes. And we see a poleward undercurrent. Does it deepen to intermediate depth and extend to 32 south or maybe even 34 south? We don't know, not yet. It also showed nicely the Agula's return current, its retroflexion in the Agula's current itself. And then I quantified the transports of both the South Atlantic current and the South and South Equatorial current and how they decrease the strength with increasing depth. And the same how they depend on the longitude with the east to west increase followed by a decrease towards the western boundary, but the latter only clearly for the South Atlantic current and not for the South and South Equatorial current. And then within the velocity or the transport plots, the maps with the vectors, there were clearly lots of areas inside the subtropical gyre with north of flow. So estimating those transports in each of those pieces and closing the balance in the gyre will take some more time. Last I showed was also the latitude dependence of the Brazil current transport with between 5 to 29 straddles in the upper 2,000 meters and about 3 to 16 straddles in the 0 to 800 meter layer. And so this is basically it. And the outlook for the future, for which I don't have a slide, is I would like to go to seasonal cycle, into annual variability on this, and also to Meridional transport integrated across the basin in the upper branch of the MOC. So those are the three big things I think this data set can be useful to do with, and it can be very useful, I think, for comparison with models. So if you have an Aussie nature one, you can compare the velocity fields. If you get the climatology right, things like that. So that's it. So I guess I have to unmute this. Well, I have to go here and actually unmute all this. I think now everybody can hear me, and it's only Roberta and she. Any questions?
It's that she's talking.
How are you? Now I can hear everybody, I hope. So there's no no reason to type.
Yeah, what I would like to say is that independent of the resources that you have and users, etc., I think the main accomplishment is to have derived from the Argo flow the three-dimensional field for the South Atlantic.
Yeah.
And in the future, I know it's a lot of work and we need funding to do that, but it would be great to extend it to the whole Atlantic.
Yeah.
It's a very valuable three-dimensional field.
Yeah. Well, since this was a seminar on the South Atlantic, I didn't mention it, but we are trying to expand into the North Atlantic. We started it, and whenever we have a little bit of time, we continue doing that. And if we can get funding for it, yay! Then we can do it a lot faster. Yeah.
Have you looked at how they compare the Brazil current transport that you estimated from the Argo Altimetry product compare with the means from the ASAP data?
Not yet, but I would like to. I would love to. Yeah.
And there is a second concept, AOML, that is just to compute, to monitor the Brazil current transport.
Yeah.
To power,
Right.
Did you see in the surface, you saw the double gyre, or you saw the gyre extending to the bifurcating to the south at the? What is?
You want to look at this?
Yes.
And you are talking which depth?
I wonder if you saw the double gyre, or actually what you saw is that at depth it bifurcates to the south.
Yeah, the bifurcation does shift southward.
South.
Yeah, yeah.
But you did, the whole gyre was seen by Diana Menezes,
Right.
not your result.
Well,
That's
it's-
excellent.
let's go back until I get there. Oh, went too far. All right, what is here is we have westward flow here, westward flow up here, and a little area of eastward flow right here. And then here, I mean, he actually has this circulation here. I don't have that. But he does have the westward flow here and the westward flow here, and not much in between in terms of solar transport to the west. And that's what is referred to basically as this double gyre structure. But you seem to have two bands of westward flow in this south equatorial current.
And the northern one bifurcates, and the southern one just goes to the south.
But it has to,
Yeah.
yeah, unless it makes some local crazy recirculation, but eventually it has to go south here.
Thank you very much.
Yeah.